In this lesson, we're going to take a look at solution concentration expressed in units called molarity. We'll also take a look at a few mathematical examples that describe calculations related to molarity and solution concentrations. Let us begin by reviewing exactly what a solution is. A solution is described as a homogeneous mixture of solute particles dissolved in solvent particles. The fact that it's homogeneous simply describes the disbursement or the distribution of particles in the solvent. As a homogeneous mixture, the disbursement or distribution of the particles would be in an even arrangement. This might also be described as a uniform arrangement. Concentration will simply be a way to express the distribution of solute particles in a ratio compared to solvent particles. The form of concentration known as molarity describes what we know as the number of moles of solute dispersed in the total liters of solution. Molarity itself means moles per liter or moles over liter. It is often expressed as capital M to represent molarity concentration. Therefore, a formula for this particular type of concentration would look similar to what we have circled. To better understand, one must recall that the mole amount of any material can always be related to a mass. Mass is typically expressed in grams. The key to understanding molarity sometimes relates to remembering how to relate a mole amount to a mass, or vice versa, a mass to a mole amount. If you recall from previous lessons, relating a mass to a mole amount would require us to turn mass in grams into mole. That always requires division by something known as the molar mass. Vice versa, by turning a mole amount into a mass, we would multiply by something known as the molar mass. The molar mass would depend upon the chemical of interest. Since the formula for molarity expresses an amount of solute only in mole amount, this relationship between mole and mass is critical for understanding. Let us take a look at a few mathematical examples to reinforce the idea of molarity. In reading the problem here, what would be the molarity concentration? We realize we're trying to calculate a concentration in this particular example. The information that is provided or given is a mass of a chemical and the volume of solution to be prepared. There are a number of ways to deal with molarity style calculations. Each will require familiarity with the formula for dealing with molarity. Molarity equals the number of moles of solute divided by the volume of solvent. N representing number of moles, and V representing the number of liters of solvent. Rearranging the formula can sometimes be an easier method to deal with it, as pictured in the triangle to the right. In this particular example, it is asking us to solve for the molarity, or capital M. We can see this would require us to know the N, or number of moles, and the V, the volume of solution. Since the words of the problem do not include the number of moles, we must arrive at the number of moles so we can use that. Once we know the number of moles, we would simply divide by the number of liters of solution prepared. This particular problem describes a chemical compound known as iron 3 chloride, which has a chemical formula of FeCl3. That is critical to determining the molar mass of this particular compound. Since the molar mass will unlock the mole amount necessary, we will need to calculate the molar mass taking into account 1 iron atom or ions and 3 chloride ions. The molar mass for iron 3 chloride turns out to be 162.2 grams, equivalent to 1 mole of iron 3 chloride. Since we are given the mass amount of iron 3 chloride in the problem of 32 grams, we need to convert that gram amount into a mole amount. When given the gram amount or the mass amount to convert it into mole amount, we would always divide by the molar mass. Therefore, we will divide by 162.2 to arrive at the number of moles necessary. This gives us a total number of moles of 0.20 moles of iron 3 chloride. What this provides for us is the N, or the mole amount necessary for the formula. Now we must read through the problem to find the volume. It describes 350 milliliters of solution, but you can notice we must use a liter amount and not a milliliter amount. If we recall that 1,000 milliliters is the same as 1 liter, we can simply move the decimal position 3 places and convert milliliters back to liters. This creates a total number of liters of 0.350 liters. We now have the mole amount of solute and the total liters of solution necessary to calculate the concentration known as molarity. Therefore, we will solve for M by dividing N by V, or 0.20 moles by 0.350 liters. This gives us a molarity concentration of 0.57 molar, capital M, representing moles per liter or mole over liter. Let us look at another example to reinforce the concept or idea of molarity. When reading this example, it asks us to solve for a mass. Reviewing the formula once again, mass is not found in the formula. There are 3 variables found in the formula: a number of moles, a volume in liters, and the concentration known as molarity, moles divided by liters. Since mass is not found in the formula, we must solve for the mole amount, or N, so we can arrive at a mass. By knowing the mole amount, we can always convert the mole amount back into a mass. Let us look at the other information that is provided or given. We see that there is a volume of 275 milliliters and a concentration of 2.5 molar. Therefore, we have information for the V portion of the formula in milliliters, which we may not use. We must convert that to liters. Recalling from the previous example, this converts to 0.275 liters. We now have the volume in the units necessary to deal with the formula. We also have the concentration, or M, necessary to calculate the number of moles. To calculate number of moles, we simply multiply, to solve for N, multiply our molarity concentration and our volume in liters. Therefore, 2.5 molar times 0.275 liters will give us the number of moles needed or interested in. This calculates to 0.69 moles of potassium nitrate. Now we know the mole amount. We simply convert the mole amount into a mass amount by using the molar mass. We factor in that the molar mass of potassium nitrate is made up of 1 potassium, 1 nitrogen, and 3 oxygen atoms. This gives us a molar mass of 101.11 grams of potassium nitrate for every 1 mole. To convert mole amount back to mass, we simply multiply by this molar mass. Therefore, we'll take 0.69 and multiply by 101.11 to arrive at the number of grams. This equates to 70 grams of potassium nitrate necessary. Let us look at one more example to reinforce the concept of molarity. When reading this example, it is clear that we are solving for a volume amount now. Therefore, we will need to know the number of moles of solute as well as the concentration of the solution. Since we see we have a mass amount, but we do not know the mole amount, we must convert this mass into a mole amount. This requires the correct formula for barium chloride, which would be 1 barium ion combined with 2 chloride ions. To convert this mass of 150 grams of barium chloride, since we are creating the mole amount, we would divide by the molar mass. The molar mass of this compound turns out to be 208.23 grams, equal to 1 mole. By simple division, we create the mole amount necessary to continue with the problem. This reveals an amount of 0.72 moles of barium chloride. We now have the mole amount needed to continue to solve, or N. Since we're interested in solving for V, or volume, we simply divide N, or the mole amount, by the concentration, capital M, the molarity. Therefore, we'll take 0.72 moles and we will divide by 3 molar solution. This will create the volume necessary, or the volume of solution that was prepared. This equates to 0.24 liters of solution. Recall that volume is expressed in liters whenever using this formula. Sometimes in a laboratory setting, it's not practical to use units of liters because measurement tools do not indicate that particular unit. It may be necessary sometimes to convert that back to milliliters, which would be more typical of liquid volume measuring tools used in a laboratory setting. Regardless, either answer is an equivalent amount and a volume of a solution prepared related to this problem. Let us simply restate some of the things that we did with the examples. In this particular example, we solved for V, or volume. To solve for volume, we would divide the N, number of moles, by the M, the molarity concentration. Since this example asked for mass, we would have to go through the mole amount to get there. Therefore, we were solving for the N. To solve for N, we multiply the concentration, or molarity, times the volume in liters. We then took the N, or number of moles, and multiplied by the molar mass to create the mass needed. And in the first example we looked at, we were solving for the molarity concentration, which requires us to know the number of moles and divide by the volume, or liters of solution prepared. The key to really understanding is to recall an old idea related to converting mole to mass amount. When converting mole to mass, we would always multiply by something known as the molar mass of the chemical of interest. Conversely, if we had the mass and we needed the mole amount, we would simply divide by the molar mass of the chemical of interest. These conversions are necessary for understanding and efficiently working with molarity concentration.